Yo, what's up guys? Baby Bear 4812 coming at you one more time. Today we have a hard problem. It's problem number 1095, find in mountain array. And this problem was first asked about a year ago being the summer of 2019 in a weekly contest. And now, as of recent being, we're in October 2020, Apple, Google, and Bloomberg have liked it. So it's not a problem that seems to have gotten too much attention, but I think it's a really good one. It's a really clever problem, and it's got a really clever solution to go along with it. If you haven't tried it already, I'd, as always, kind of suggest pausing it, then coming back, and we can go through it together. But it's a really good one, and I think we'll have a good time solving this one. So to give it a quick read, we're told that an array A is a mountain array if and only if, so it's at least of length 3, and there exists some I where I falls between 0 and the length of the array, such that essentially I is greater than all the elements that precede it and is smaller than all the elements that succeed it. Essentially it's saying it looks like a mountain. So you start with, trying to get the side right, so if we start from the left hand side, we're going to start creeping upwards, and we're going to be strictly increasing, and then we hit a peak, and then we strictly decrease. All right, so it looks like a triangle or a mountain. Make sense? So we're given a mountain array, and we need to return the minimum index such that mountain array dot get of index equals target. If such an index doesn't exist, we return -1. Okay, so that's fine. We'll get a bit more information on this, but we're told that we can't access the mountain array directly. We can only access it using the mountain array interface. We're given an API. We're essentially told that we can do two things with this array. We can say mountain array dot get k, where k is the index on a 0 indexed array. And secondly, we can say mountain array dot length, and that doesn't take any parameters, and that will return the length of the array. They do tell us, this is where things get interesting. They tell us submissions making more than 100 calls to mountain array dot get will be judged wrong answer. Also, any solutions that attempt to circumvent the judge will result in disqualification. Basically, what it's saying is this. If we get any sort of array, and this one, you'll check the constraints, they go up to length of 10,000. So how you can really hurt yourself here is if you try to do a linear walkthrough, because that's the trivial solution. You know, if you're in an interview, you can mention that's a possibility, but the reason you don't want to do it is because that would be ultimately trivial. You can just say, well, let me start at the beginning and look through every single element, and the first time I find my target, I'll return the index that I was at. So there's got to be a smarter way to do it. And here, so we're told we can't do more than 100 calls. We're given a size of 10,000. So think about it. We'll jump into it, but what's a quicker way to sort through or search through arrays, especially when they kind of take a certain format, all right? So that's to get the brain turning, and we'll jump into the details in a second. But just to give you a concrete example, we're told, we're given this array of 1, 2, 3, 4, 5, 3, 1, and the target is 3. What we return is the index 2, because that's the first time that we see the target come up. So 3 exists in the array at index 2 and 5, but we need to return the minimum of the 2, which is 2. If we get a case like this, where here the peak is 4, here the peak was 5, by the way. This is our peak, so we're increasing up to the 5, and then we drop off to the 3 and 1. If our target is 3, the 3 is not in here, we return a -1 because it's not in there. All right? I think that's pretty straightforward. The parameters we're given as the target and the mountain array, which is an instance of this class. All right? So I'll kind of clean this up just so it looks a bit neater. And with this class, these are the only two things we can do. So again, I'll move this because we do have it in the instructions here, but I just wanted to make that clear, all right? So let's think about how the heck to do this. Well, as I mentioned, we can do a linear walkthrough. So technically, I can start here and say, is this a 3? No. Is this a 3? No. Is this a 3? Oh yeah, okay, cool. We found a 3, and then we return index 2. The issue is we can only make up to 100 calls using the get function, but we can't say index of, give me index of 0, then give me index of 1, then give me index of 2. If we do that more than 100 times, and remember, the array can be up to length of 10,000, that's not allowed. So we think to ourselves, what's another way to search through arrays without walking through them linearly? Well, if we need to do it in a much more optimal way, the answer is always binary search. Now, you may be asking yourself, or if you're not, you're about to learn something new, but you may be asking yourself, how do we possibly binary search through an array that's not sorted? And so, for those of you who weren't aware, we can only do a binary search on an array if it's sorted. However, there's something nice that we can notice here. this array looks like this. It's a mountain array. All the arrays we get are going to be mountain arrays, and they're not going to have any plateaus. So we're not going to have a case like this where we kind of hit a peak and then go down, and maybe there are plateaus and numbers repeat. That doesn't happen in a mountain array, okay? Based on what we were told in the description. So technically speaking, what I'd argue is, sure, this isn't strictly speaking sorted, either strictly increasing or strictly decreasing, but this looks sorted to me. 1, 2, 3, 4, 5 is definitely sorted, and then 3 to 1 is sorted as well. It's sorted in decreasing order, but it's sorted nonetheless. So one of the key pieces of information to understand here, the first kind of revelation you need, maybe revelation is a bit of a dramatic word, but the first thing you need to be aware of in order to solve this is to realize that a mountain array is sorted. It's kind of sorted in increasing order and then in decreasing order. If you can get that, that'll be the first piece of information you need. So first thing we need is, okay, so it's sorted this way, then it's sorted that way. Now, if we want to do a binary search, we need to do it on strictly a sorted array, meaning that I can binary search this, and I can binary search this, right? And if I can binary search those two separately, all right, that's wicked. Ultimately, I'm looking to return the smallest index, or the first occurrence of this target number that we're given. What does that mean? Which side should I find first? Should I look in the left-hand side of the array or the right-hand side of the array? Well, again, if we're looking for the first one, or the smallest index, the first thing we want to do is actually search in here. We need to do a binary search on the left side of the array. It may not be the left half. You know, you can see we've got a length of 5 here and only a length of 2. So it's not like we're split 50-50. But the first thing we want to do is to say, well, let me look at this first piece. If I don't find it in there, if I do, let's return it, and, you know, cool, everyone goes home happy. If we don't find it, let's check in the second half of the array. If we still don't find it there, then we return a -1. All right, the one piece of information I've kind of omitted here is the fact that, well, how do we find the 5? Right, how do we actually go about finding the peak? That's going to be the first thing. If you can realize that the first thing we actually got to do, apart from, you know, seeing that it's sorted twice, the first thing that we need to do is we actually need to find the peak. Once we find the peak, then we can go ahead and do 2 separate binary searches on the left and right hand side. So our number 2 step would be search left, capital L for short. Our third would be actually to search right. We search left. If we don't find it, then we're going to search on the right. If we don't return anything here at this step, or we don't return anything here at this step, ultimately what we're going to have to do at the end of the day is just going to be to return -1. All right. To actually find this peak, again, this could be a very long array. We can only make 100 calls to get. So the way that we're going to do this one, once again, is actually going to be through a binary search. We're going to find a way to find the peak using a binary search, which is unintuitive because it's like the first thing that I said was we need to be sorted to binary search through an array. And that is true, but what we're going to do is we're actually going to find a way to still get to it. It won't be botched, it won't be dirty in any way. It'll all be fully legal, but what it'll do is it'll require a slight twist on the traditional binary search. So maybe I'll put binary search with a little asterisk here, okay? To search on the left-hand side, we're definitely gonna have to do a binary search, and on the right-hand side, we're gonna have to do a binary search. This problem is a triple binary search problem. I don't think you see those often, and I think putting together the fact that it's sorted this way and that way, that you need to find the peak and then search the 2 sides separately to make it a triple binary search problem, makes it a really cool problem. And to get the solution that way is, like I said, I think it's kind of intuitive, but then I'd argue at the same time, if you do a lot of these problems, or maybe I should say this, if you've done a lot of these problems, maybe this will come to you intuitively. If you're in that in-between range where you haven't done too many, this is probably your first time coming across a binary search where you're like, oh damn, like maybe I need to do this 3 times in one problem. And I think that makes it slightly tricky if you're kind of in that intermediate stage. But I think the logic is more or less straightforward, and we're probably in a good position right now to pause this and then jump into the code and try to make it happen. So first thing that we set out, maybe I'll write the steps down here as well so we can really organize our thinking. Our first step is going to be to find the peak. The second step is going to be search left side of array. The third is going to be, if not found, search right side of array. Step 4, maybe this is a bit overkill to mention this, but if not found, or to split it out as its own step, return -1. So strictly we can return -1. That step is a one-line solution. We're not going to do any error checking here because we're told in our constraints that we'd have a legitimate target and an actual properly sized mountain array, so nothing of length smaller than 3. So that's good. And what we said is we got to do binary search on all 3 of these. I think steps 2 and 3 are pretty vanilla. To get the first step is maybe a tiny bit trickier. So why don't let's start with that one, and then we'll jump into the next 2. First thing that I want to say is, actually more than anything, what I think I'm going to do is I'm actually going to get the length of this mountain array. The reason I want to do that is because when we're setting our bounds, we're definitely going to use that more than once, and so I'm not always making the call to this API. And we're told this is the function right here. What I'll say is I'll call the variable length, and I'll set it equal to mountain r.length. All right. So we've got that there. Now, what do we do here? We essentially want to find the following. We want to find the midpoint, the peak of this actual function. We know it's somewhere, or not of the function, sorry, of the array, and we know that it's somewhere within the 2 bounds, the left and the right bound. So what we can go ahead and do is this. We can set the left bound equal to 0. We can set the right bound equal to the length of the array -1, so that we end up at that final index. And then we're going to do the following. We're going to jump into our standard, or sorry, let me actually got to initialize a peak as well, so I don't know what it'll be. I'll set it to none. You can set it to -1. It really doesn't matter. I'm initializing here. And then what I'm going to do is I'm going to say while left is less than right, do cool stuff. So I'm not going to get into any of the code here just yet, because I know there are going to be some questions in the comments, or I presume there'll be, as to why I'm doing less than right and not less than or equal to, because sometimes we all jump between the two, as in terms of like what we need to do. As a basic rule of thumb, if you're not returning anything, which I'm not here, you'd set the condition to be left is less than right. And when we walk through the example, you'll see why that ends up working out. If you are returning something, then you want to do left is less than or equal to right, because then we actually want to strictly compare when the 2 pointers are pointing at one object, whether or not that's the target of interest, okay? So what I've got to do now is this, I've got to find my midpoint right now, and I'm going to say that again. So midpoint typically can be this. We can say right plus left divided by 2, as if we're finding the average of 2 numbers. One way you can slightly improve this is, to avoid a potential integer overflow. Integer overflow would happen if you get 2 really big numbers for right plus left, and when you add them together, they get super big, and then it just becomes too big to handle for the language, and you're out of luck. With a bit of, I guess, mathematical gymnastics, what we can do is essentially say something like, let me think, this could be right plus left minus right divided by 2. I'd encourage you to write down the fractions and try these out step by step if you don't believe me. Essentially what you'll get is you get right plus left divided by 2, and I'm just kind of giving you guys a really quick proof just so you believe me. That's equal to right divided by 2 plus left divided by 2, okay? Well, this side over here, we can say that's just equal to right minus right divided by 2, and all that plus left divided by 2. These two have the same denominator, so I'm left with right plus left divided by 2 minus right divided by 2, and ultimately right plus, left minus right divided by 2. Okay, that's why I'm doing this again, to avoid the integer overflow, and this is the quick proof as to why it works. So I just wanted to drop that super quickly. I didn't mean to go on a tangent. What I'm interested in now is this. This is the middle index, all right? Let's take a look at the middle index. So in this example, this is my left, this is my right. This is going to be my middle index. How do I know if I'm at the peak or not? I can try to find my peak by saying the following. If my peak plus 1 is increasing, if my mid plus 1 is an increase, so 4 to 5 I'm increasing, then 4 is definitely not my peak. So I'm going to have to search in the right half of my peak. Now I'm going to have to jump into here and look for my peak in here. If I'm on a point that's increasing, so if I find myself here, I need to keep edging closer and closer while my mid plus 1 relative to my mid is increasing, I need to keep edging closer until I get to the point where I drop off. Once I drop off, and that'll be this point right here where I drop off from 5 to 3, then that's going to be where our peak is. Similarly, if I'm on the other side of it and I'm here and I realize that I'm dropping off immediately, I need to edge backwards and keep going backwards until I'm just larger than this side over here. All right, and that's the basic logic for how we're going to go about finding the mid, or the peak, excuse me. What I'm going to say is this. So I'm going to have to say, if mount an array, we want the value of it, right? If the value of it at mid is less than the value at mid plus 1, like I was just mentioning, then what we know is that we need to look at the right half, right? The center, right half for you of this array. And what that tells us is that we're going to have left we can increase by 1, and also mid I want to increase by 1. Or excuse me, I don't want to increase the mid by 1. I'm going to set the I'm not increasing it by 1. Left is going to equal mid plus 1. Excuse me. So brain freeze. I'm also going to set my peak equal to mid plus 1. I'm going to set it equal to exactly where my left pointer is. The reason I'm going to do that is because ultimately, and we can walk through the example at the end, ultimately what's going to happen is when we squeeze the two numbers together, if we're not in this case, so if we're in the opposite case of this happening where we're kind of greater than, so we want to move back upwards, what I'm going to do is I'm going to set right equal to mid. And so by doing that, what will happen is when you walk through the example, kind of, I'd urge you to do it by hand. I was going to say maybe I'll do it with you, but I think the video would get very lengthy. What you'll find is that we'll keep squeezing the right into the mid until they overlap each other. Once the left and right overlap each other, this condition will break. And since the peak was set equal to what the left was, then, well, they're only going to meet where the peak actually is. And so that's why I'm actually going ahead and setting the peak to mid plus 1, which is exactly what I'm setting my left pointer to. All right. So I hope that's clear. Let me know down below if that's not very intuitive. I would suggest just taking this example and walking through it step by step on paper. It won't take you more than a few minutes, and it should clarify why we're doing that. Now, for the second step, we need to search the left side of the array. So now we're into slightly more familiar territory. We can set our left boundary equal to 0 because, again, we're on the left side of the array. And the right-hand boundary actually is going to be equal to the peak, right? Because we know where the peak is now. The peak is here at the 5, right? So we want to search this array. And this is now going to be a standard binary search to see if we can find the target number, right? Standard binary search to see if we can find the target number. So what I'm going to do is I'm going to say while left is less than or equal to right, this time because I'm going to be returning a value potentially, I'm going to say this. Mid is equal to right plus right, or excuse me, left minus right divided by 2, right? So same type of tactic as above. And now I essentially say this. I say if, maybe let me do this as well. I'm going to be using this number multiple times, so maybe I'll call it mid num is equal to mountain underscore r of mid. No, I'll call it mid. Okay, mountain array of mid. So not of dot get. Excuse me. And I realize I made that mistake here as well. I'm sorry if you guys are screaming at me about that. That was syntactical, but the logic still holds, okay? Mountain array.get of mid. So now we ask ourselves this. If mid num is equal to the target, then all we want to do is return mid, right? This part right here. Maybe just to be clear, I'll call it mid index just so like it's super crystal clear what I'm actually referring to with mid. Otherwise, we want to say if mid num is less than the target. If the middle number that we have is smaller than the target we are looking for, then I want to search the right half of what I've just been looking at. So I want to take left and set it equal to mid index plus 1. Okay. Otherwise, and I know this can be an else statement, but just so we can spell the logic out. Otherwise, if the middle number is greater than the target, that means we went too big. And we need to shorten our right boundary and set right equal to mid index minus 1 so we can search the left half of our broken down array. And this is all just standard binary search, right? I'm not reinventing the wheel here, I promise. So if we essentially don't end up returning anything here, we're going to jump into this third step here of trying to search the right side of the array. This is going to be just about identical, okay? Instead of, so left, we're gonna set the peak +1 because we've already kind of searched from 0 to peak. Now we wanna search from peak +1 until right is gonna be length -1. So right until the end of the array. We're still gonna do while left is, while left is less than or equal to right. We are gonna calculate mid the exact same way, and I'll do, actually, you know what? I'm just gonna copy and paste this code. There could be a clever way to modularize this. Let me know down below if you guys know of a really nice way to put these two together. This one and what we're about to put in, but I'm just gonna copy them, at least for the time being. Same thing, I'm gonna say here if mid num is equal to target, we're gonna return the mid index. However, if mid num is less than target now, we gotta be careful. Because what we're doing is we're looking through a decreasingly sorted array, not an increasingly sorted. What that means is that we're gonna have to say that right is equal to mid index -1, if this is the case, if the middle number is smaller than the target. We're essentially switching these two conditions. So, as well, if the mid number is greater than the target, then we're gonna say left is equal to mid index +1. And the reason that is as follows. Let's say we had something like, I have something 6, 5, 4, 3, 2, 1, 0. All right, and this is left, this is right, this will be mid. Perfect. If I find a number, so we said if the and let's for example say that our target is equal to 2. All right, so this is the number I'm looking for. Our middle is 3. Our middle at 3 is larger than the target. Since it's larger than the target, I now want to search in this half of the array, all right, which is the right-hand side now because we're in decreasing order. That's why left is going to end up being mid +1, right? And this is going to be our new mid. That's why left ends up being mid +1. And then the converse also holds as it is. And so that's all there is to it. I say that as if it was like super quick, which it wasn't. But I'm just going to try to run this really quickly and make sure that I haven't messed you guys up. Length is not defined, which means that I made a stupid typo, which I didn't catch the first time because we never got there, and there we go. So this implementation is the same as this one that did 20 milliseconds, which was something like 98th, 99th percentile. So it's a strong solution, and I'm going to move this over a bit so you guys can see. Just to show you the whole solution one more time, length I just had so we don't have to keep doing this function call all the time. Our first step was to find the peak. Okay, once we went through actually finding the peak, we could then say I've got two partitions of this array. I've got a left-hand side of the mountain and a right-hand side of the mountain. We will first search the left-hand side of the mountain to see if we can find our target because that's where we'd find our first occurrence. If we find it, cool, let's return it. If not, let's try searching in the second half, or not even half, sorry, the right side of the array or the mountain array. Here we have to be a bit clever because it's now sorted in decreasing order instead of increasing, but no matter, that was a quick fix. If we find the index, or if we find the number, excuse me, return the index, cool. Otherwise, if that also fails, last step was to return the -1. That's all the code from start to finish. I hope you guys enjoyed this. I hope you guys found it helpful. Again, I think it's somewhat intuitive to kind of get to the answer, but it's not obvious by any means. I thought it was a cool problem. If you enjoyed it, if you learned something, like, comment, subscribe, share. Yeah, send it to all your friends, all your buddies, all your teachers. Yeah, I'm like running out of people to jokingly tell you to send these videos to. So I'll pause it there for now, and I'll see you guys in the next video, all right? Peace.